Good evening, everyone. Hope you're having a fantastic week. I'm recovering from a pretty wicked cold today, so will this be a good idea? Will it not? Let's see. Let's see how long we can go for, and I'll try my best not to clear my throat directly into the microphone, but no promises. I'm sorry in advance. Let me know, as always, if the audio is not quite right, but I don't have any housekeeping. Let's get right into it, hey? We're working through the Cryptopals series at the moment, which if you've missed the first 7 or so of, they're on YouTube. Links down below somewhere. For those tuning in from YouTube, hello to you. Last stream we polished off set 2. We revisited revisited cut and paste. Because I realized during editing it was exploitable the hard way that we'd avoided doing. And then 15 was a no-op for us. Our PKCS 7 unpad, it was already operating in a strict mode, and we worked through the CBC bit flipping attacks. I've been really looking forward to this one. We're on to set 3. It's the next set of block cipher cryptography. Apparently it's moderately difficult, so we've been struggling enough so far. We'll see how this goes. It includes a famous attack against CBC, which I think is the padding oracle, which is a lot of fun, and a cloning attack on a popular RNG, which will be the Mersenne twister. Not sure how to pronounce that. We'll figure that out as we go. And we've reached a point where all the challenges, with one possible exception, could be valuable for real-world crypto. Hooray! We're past the Babby's first stuff. So, CBC padding oracle. It is apparently the best known attack on modern block cipher cryptography. We need to write 2 functions. It's CBC mode. The first function should choose at random one of these 10 strings. Generate and save an AES key. Do the padding, which our encryption function does for us. CBC encrypt it. Providing the call of the cipher. What? The function should generate the key, pad the string, and return the ciphertext in IV. That makes sense. The second function should consume the ciphertext produced by the first, decrypt it, check the padding, and return true or false. That might be a bit tricky with the way we've set things up, but we can see how we go. So this is approximating CBC encryption as it's deployed server-side. The second function models the server's consumption of an encrypted session token. Okay. Turns out it's possible to decrypt the ciphertexts. This challenge is worded weird. So we need to pick at random one of these 10, encrypt it, give a decrypt oracle that has strict padding checking, and it's possible to use the oracle to decrypt the ciphertext. It's just worded kind of funny to me. The decryption is going to use a side channel leak within the decryption oracle. The leak is the error message that the padding is valid or not. It's telling us to use Google and figure out how the attack works. It's very well known. The fundamental insight is that the byte 1 is valid padding and occurs 1 in every 256 trials of randomized plaintext. 2 by itself is not valid padding, but 2 is valid padding. 3 is valid padding. So if you can assume that if you corrupt a decryption and it has valid padding, you know what the padding byte is. All right, let's get going. Hey, we'll figure out the subtleties of what it wants as we go. So this is set 2, challenge 17, CBC padding oracle. Set 2, challenge 17, CBC padding oracle. Do our boilerplate. Cool. Main does nothing, and run main. Cool. Let's stash these in a data file. This is set to challenge 17. Set to challenge 17.text. Alrighty. So CBC padding Oracle. Oh, no, that's a class. So I'll create a class for our Oracle. How did I mess that up? It's going to have an initializer. So the Oracle is going to need, a plain text, which is bytes. And that's it. So we'll set our plain text to the plain text. Plain text is bytes. I think in main, I think the caller, the creator of this Oracle should be the one that parses those lines and picks one at random. So pick a line from the challenge input. So we'll open the file, data / set to challenge 17, open it as text. Let's pull in our secrets. Do we get a choice? Yep, okay, so secrets gives us choice. So lines is going to be f.read lines. Does Python give us like a stupid empty... Oh, it gives us like the trailing new lines on it, doesn't it? Let's just print lines and run this. Yeah, so we get new lines at the end of each of these, and the last one doesn't have a new line. That's cool. They're all base 64, so we'll just map strip across those. I think that works, doesn't it? No, it doesn't work. Lambda x is x.strip. Just to get rid of that trailing new line on each line. There we go, that's gotten rid of the new lines. The plain text is going to be choice over lines. So secrets.choice just basically picks a random element from a collection. And if we just print PT and run this, we'll get a different one each time. Yeah, there they go. We need to pull in base 64. We'll do base 64.decode over this to give us bytes. Why are you squiggly? B64 to code. Cool. And our Oracle is going to be the Oracle over the plain text. Cool. So we've got an Oracle that basically has a plain text. @Wolf, what does this button do? It puts your message in fun colors in chat. How cool is that? Rightio. So the Oracle's going to need a key. So we need to set up our block size. So block size is 16 for AES128. Self.key is going to be pulling our random token generator. Token bytes over the block size. Then I think we just need like a decrypt and an encrypt, right? So encrypt takes no arguments. Just returns. I need to pull in our encryption stuff from utils, import the CBC needfuls. encrypt of, we need an IV. So plaintext is self.pt. Key is self.key. IV is to do. So IV is token bytes to the block size. We don't just return this, we need to grab it and return the IV concatenated with the ciphertext. So we've got the output of the encryption is IV and then the ciphertext smacked right on the end of it. Then we've got a decrypt, which this does take a ciphertext, which is bytes. Oh, this has to return bytes. Decrypt takes a ciphertext, which is actually like the IV and the ciphertext smashed together. It is going to do ciphertext chunks. So we've got to chunkify that. Pull in our chunkifier. So the chunks is going to be chunkify the ciphertext to the block size. And the IV and the ciphertext is going to be chunks 0 and empty bytes dot join over the rest of the chunks. Why are you yelling at me? This is still a generator, so I need to realize that. Cool. Now the decryption is going to do plaintext equals CBC decrypt, where the ciphertext is CT, the key is self.key, and the IV is IV. And return the plaintext. Oracle built. So with our Oracle, we can do ciphertext equals oracle.encrypt. And the plaintext is going to be Oracle. Hang on. Where have we gone wrong? Because the plaintext is just oracle.decrypt and the challenge is done. So what have I messed up? The first function should pick one of those at random. The second function should. The decrypt function doesn't actually return the plaintext. All it does is return true or false depending on whether the padding was valid. Okay. So this decrypt is actually decrypt and check padding. And where is this refactor going to ruin stuff? It's going to ruin stuff in another file. Thanks, I hate it. Let's just manually refactor. Decrypt and check padding. It just returns a bool. So I'll fix that in a minute. This here is decrypt and check padding. Call that res, and then we'll just print the res. So in here, we want to try. We don't need to capture plaintext anymore. We just need to try to do the decrypt. That's all we need to do. I'll fix this in a moment. If it raises an exception, we return false because the padding was invalid. Else we return true because if it's successfully decrypted, no padding exception. Now we never want to catch exception, but from util we actually created a padding error type exception, so we can just catch the padding error. So our decrypt function actually doesn't decrypt and return the plaintext. It just basically returns yes or no. Yes, the padding was fine. No, the padding was bad. So if we run main, we get true. Hooray! The padding in the ciphertext, as was returned by the oracle, is good padding, as opposed to if we this will probably return false. If we do, if we just flip the last bit of res, it will break the last block catastrophically, actually. If we go to our CBC diagram, CBC, decryption's down the bottom here. If we flip this bit here, this block cipher decryption is going to catastrophically change its output, and then this plaintext will catastrophically change and will probably not have valid padding. So if we do res equals, no, that's fine. We'll just duplicate this here. And we will do ciphertext equals ciphertext up to the last byte, and append onto it the bytes of ciphertext, the last byte. And because Python's funny when you start slicing bytes, you got to do this. You know, if you just pluck a single thing off of the bytes, you get an integer. So we need to turn it back into bytes. Whereas if you do like a range, it comes back as bytes. Now inside this bytes here, this ciphertext -1, we'll just XOR it with 1 to flip the lowest bit in it. If we rerun main, doing decrypt and check padding over the original ciphertext as it came back from the oracle gives us true. If we go and corrupt the last bit of it, all of a sudden the oracle decrypt and check padding is unhappy. It returns false. So we don't exactly have the easiest way to write tests for these functions, but that output there makes sense to me. So if we just have a quick read of this to make sure it looks fine. The class has a plaintext. The class also has a key, which is bytes. So when you initialize an instance of this class, we set the plaintext and we set the key. The key is just random bytes. Encrypt generates a random IV, does the encryption of the plaintext with the key, smashes them together and returns them. The check padding decryptor takes ciphertext, which is really IV and the ciphertext concatenated, chunks it, snaps off the IV, and then leaves the rest of it, which is the ciphertext, tries to do a decrypt over that ciphertext with the key and with the IV it snapped off. And if this raises padding error, we return false, else we return true. Looks good to me. I don't know if there's an easy test case we can write for that, but it will do. Now we've got to do the hard stuff. Now we've got to basically intelligently flip bits in the ciphertext and use this oracle that just tells us whether the padding was valid or not to basically leak the plaintext. Hooray. I'm kind of inclined, for development purposes, to always use the same plaintext. Just that way we get consistent results. It's kind of cheating because we were told here to pick a random one. But I'm okay with this type of cheating, to at least make our development consistent. So we'll leave ourselves a comment to come back to this. And instead of choice over lines, we'll just take the first line, line 0. Oh, goodness. Okay, padding oracle. Now I've got to remember how padding oracle works. It's basically, I think, to do with Because you've got this weird like feed forward behavior in CBC where this block of ciphertext is XORed into the output of this decryption. And this is where our padding is going to be. One more bit of housekeeping. While I was tidying up the code before I pushed it to GitHub, I did change the way that our PKCS7 unpowder works. It's not really that consequential, but I just added a check to make sure that it doesn't end in a null, because that is illegal per PKCS7, I'm pretty sure. A lot of software does allow the last byte of PKCS7 padding to be null, which means like no padding. And that breaks a lot of the it breaks a lot of the padding Oracle tools out there. I recently had to solve a CTF challenge where it was kind of like it was a bug, and the last byte of the padding was allowed to be 0, and it caused basically all the unpadding, all the padding Oracle tools to break. So just I did change that since we wrote this function. Oh, cool! We got someone being a nuisance in chat. How do we yeet? Gone. Bye. Cool. So it's got something to do with flipping a bit, basically modifying this last byte of the second to last block of ciphertext until you can cause this byte here to become 1. Because let's say that the last block used to look like this. Let's sketch it out. The last block. So let's say it was hex 05. There would have been 5 of them. 1, 2, 3, 4, 5. And we started with like 11 characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that could be what the last block of our plain text currently looks like. We don't know for sure, but it could be that. It could also be that. We don't know. But if we start flipping bits in this second to last block here, such that this ends up as being 3, we're going to get an error because the PKCS7 unpowder is going to see that this is a 3, look at the last 3 bytes, see they're not all the same, and raise a padding error. If we cause it to be 2, same thing again, it would look at the last 2 bytes, see that they're not both the same, raise a padding error. Could be FF, and it would look at the last 255 bytes and see that they're not all FF, and raise a padding error. But if we set this to 1, the unpad is going to check to see that the last 1 byte is 1 and be like, yep, looks good to me. And we'll start getting true. So at that point, we can actually figure out what the last byte of the plain text was. Because whatever we had to do to the second to last block, whatever we had to do to this poor byte here at the very end of this second to last block, XORed with 1 is going to be what used to be there. Is that right? I think that's right. So we can figure out what the second to last we can figure out what the last byte of the last block was. Coincidentally, we can then know what the last n bytes were because they're all going to be the same as whatever this padding byte was. So now we can cause this to be 1 and stop getting padding errors. And then we can target this one. Actually, what we'll do is we'll then basically stop causing this to be 1 and start causing this to be 2, which I'm pretty sure we'll be able to do once we know what it was. And then we start doing the same to this one. We start flipping bits in the second to last byte at the second to last block until this becomes 3. We're going to get an error because these aren't both 2. If this becomes 1, we're going to get an error because these aren't both 2. But as soon as this starts being 2, we're going to know what we had to do to this to cause that to become 2. We can XOR that with the number 2 and find out what the second to last byte of the last block was. And then repeat until profit. At least it's something like that. Anyway, let's start playing. So let's create a leak plaintext from padding oracle function. And what does it take? It's going to take an oracle. It's going to take a padding. It's going to take an oracle. Keep it simple. Which is a callable over bytes, which gives us Boolean. Yeah, gives us a Boolean. We're also going to take an IV, which is bytes, and a ciphertext, which is bytes. And it's going to return bytes, ideally, in the end. So we'll pull in this name here. Let's document this. So Oracle, a function which, oh wait, no, the Oracle needs to take bytes and bytes. A function which takes an IV and a ciphertext and returns true if the padding was the PKCS 7 padding was correct, else false. The IV, it's kind of self-explanatory. The IV ciphertext is the ciphertext. How about we change it? A known good IV and CT is a known good ciphertext. Returns the plain text corresponding to IV and ciphertext. Yeah. Now, I have chosen to kind of break up IV and ciphertext and the IV and ciphertext going into the padding oracle, because even though our oracle does what I think is a pretty common pattern of smashing the IV and the ciphertext together and then unpacking them, I don't know that all victim oracles have the same shape. And so to be more portable, I've chosen to take the IV and the ciphertext separately and to give them to the oracle separately. Which means that we need to basically write a bit of an adapter for our oracle so that it can be given to this function. Let's just comment this out for now. Let's create a function called wrapped oracle, which takes an IV of bytes and a ciphertext of bytes and returns Boolean. And we basically wanted to return the oracle. No, hang on. Wait a minute. Feels kind of gross, but this wrapped oracle will just reach out into the parent frame and grab the oracle. Return the oracle over IV plus ciphertext. Why are you yellow? CBC. Oh no, oracle dot decrypt. Yeah, cool. So now we can run the leaker given the wrapped oracle. Let's flesh this out. Oracle equals that wrapped oracle. The IV equals, we need to do this. Actually get some ciphertext out, and then we need to unpack it. Let's pinch this line here. Nope, let's not. The chunks is going to be chunkify the ciphertext to the block size. Realize it as a list. Then the IV and the we'll overwrite the ciphertext, that's fine. The IV in the ciphertext is going to be chunks 0 for the IV, and then the rest of the chunks for the ciphertext. Cool. So now our leaker can be given the IV, and the ciphertext equals ciphertext. So that's going to return the plain text to us eventually. And then we can print the plain text. Alrighty. If we run main, not a lot happens, but at least it doesn't blow up in our faces. So, I guess the first thing that our leaker should do is just do like a check to make sure that the oracle seems to be behaving properly. So if we call the oracle over the IV and the ciphertext, if not res, we're going to raise a value error. Oracle is returning false for IV equals the IV, and the ciphertext equals the ciphertext. Bad oracle or bad IV ciphertext. Okay, good. At least we know that our oracle's behaving now. So, now what? I guess we implement that simple case, right? We're fiddling with this last byte of the second to last block. Can be used until this gets to be 1. I guess we can just kind of prove that concept for now and see where we go from there. Okay, so let's do for I in range from 1 to 255. Let's do this. Let's do CT chunks. Let's just chunkify this CT for now. Chunkify the CT to the block size. So if I in the range 1 to 255, so because range doesn't include that last value, so this gives us all the possible modifications we can make. Actually, we probably should do iron range 256. Let's just grab the raw values. CT new is going to be CT chunks up to the third to last block plus the CT chunks of the last block plus the second to last block plus the CT chunks of the last block. Oh, no, this is a mess. Yeah, so this is the one here that we want to mess with. Why are you complaining? We need to list this out. Why are you complaining? this needs to be, because it's range. Empty bytes.join it. Yeah. So this is the one here where we want to kind of spike that last byte. So what we'll do is for that chunk, we won't include the last byte, but we will tack on bytes over I. This is a mess, but it's going to need to be a much different shape for the actual attack, but this just proves part of the concept. So the new ciphertext is going to be everything but the second to last and the last block. Everything but the last byte of the second to last block. This byte here that we're iterating over. And the last block. And then if we run the oracle over that, IV, and then the CT new, if that has good padding, let's just print I. Now there is a weird case where this, I think this can return 1 or 2. It can print 1 or 2 values. And we got 2. We got 2, we got 2, we got 2, we got 2. Now, so we're in the we're in a weird edge case of padding oracle stuff, and I've lost my diagram. I think this means the fact that we're getting 2 things here is, yeah. Oh, I was hoping we wouldn't have to handle the edge case so quickly. I believe the last block currently genuinely looks like this. 14 characters, hexo 2, hexo 2. And by spiking the last byte of the second to last block, we're causing one of 2 things to happen. Hang on. Doesn't matter if it's hexo 2, hexo 2. It could even be hexo 3, hexo 3, hexo 3. Yeah, that also works. Put it this way, we're either causing it to be 1 or we're causing it to be n, where n is the number of bytes of padding. So this will probably actually always return or print 2 values. Whether we're spiking this to be 1, that's valid padding, because the last 1 bytes are the value 1. Or 3, in which case the last 3 bytes are 3. So that actually makes a lot of sense why there's 2 values being printed here. The Reckless, what's going on here? Welcome. We are working through the Cryptopals Cryptography Challenge series, exploiting CBC padding oracle scenarios, I suppose. So we've gone and built ourselves an intentionally vulnerable CBC encrypt and decrypt widget, and now we're beating up on the decryption function to implement the padding oracle attack. We haven't gotten very far just yet. I'm still trying to re-jog my memory as to how padding oracle works. Yes, the Matrix has you indeed. Follow the white rabbit. Blue pill or red pill? Purple pill. The Reckless, we found out the Reckless has taken both pills. Mix them both, there you go. Good work. So it's, yeah, this is printing 2 values and that's fine. Obviously this is where my understanding of padding oracle extends to, right? Because normally, what do I normally use for padding oracle? There's 2 things. NCC Group actually basically has a published solution for the Cryptopals Padding Oracles challenge, and I'm going to avoid focusing on what this is saying because I'm trying to do it from scratch. But it actually has basically code that solves this challenge, and it's really nice code. It's actually where I got the idea of writing functions that take callable oracles. That way you can basically, like if you've got like a web CTF where there's a vulnerable cookie thing, you can write a function which basically exercises that, wrap it up in an oracle and give it to the code in here, and it just works. It's beautiful. And Padre is the other one. Padre padding oracle. I also often reach for Padre. It's super quick because it like parallelizes it and stuff. So that's why I'm getting stuck where we're getting stuck here, because normally I just reach for off-the-shelf stuff that implements it, and they're both good enough tools that you don't need to understand how they work, but it's always good to understand how they work. The Reckless is trying to learn to code with no experience. Where can you start? Aha! I'm a really big fan of Learn Python the hard way. First of all, I'm a big fan of Python as a language. I think there's a lot to like about it. But Learn Code the hard way, they've got one for Ruby. They've got one for Python 2. Don't learn Python 2, it's dead. They've got one for C, SQL. Here we go. Learn Python 3 the hard way. I'm pretty sure like a whole bunch of the course is online for free. But I think at some point, it's basically like if you want the rest of it, go and buy the book. And it's... I haven't bought the book. I did like the old Python 2 the hard way, back when it was all online for free. But I haven't hesitated to recommend that book for people who want to learn how to code. Learn Python 3 the hard way is a very good course. Well, Learn Python 2 the hard way was a good course. I'm sure Learn Python 3 the hard way also is. So the Reckless, that might get you started. Yeah, Learn Python the hard way is like absolute beginner stuff. Like if you look at their first lesson, they walk you through getting Python set up on your machine, whether you're running a Mac, Windows, Linux, like very much beginner stuff. And a good first program is just printing text. So yeah, Learn Python the hard way is absolute beginner stuff. You are welcome. I hope it serves you well. And I hope you enjoy it. I very much enjoyed it when I did it back in the day. One more thing that jumps out to me about padding oracles. Everyone talks about a zeroing IV. The Reckless with Linux be best. If you're just learning to get started with Python, honestly, whatever you're comfortable running is completely fine. Python, if that's how you want to choose to start, works just fine on Windows, Mac, and Linux. I run Linux. I love Linux, but if you're starting out with something, just choose one thing to work on at a time. And Python's a great thing to get started with, or any programming language. Do it on the machine that you're most comfortable with. If you're comfortable on Linux, go for it. If you're on a Mac, go for it. If you're on Windows, just go for it. In terms of a Python IDE, a lot of people like Visual Studio or Visual Studio Code. I run PyCharm, and I'm pretty sure PyCharm has like a community edition for free. PyCharm's got a free community edition, so I really like JetBrains PyCharm. It's what I'm using here. But VS Code is another popular choice, and again, both of those run on all platforms. So a lot of people talk about zeroing IVs when it comes to padding Oracle, which, you know, once we learn what to XOR into the second to last block to make this be like all hex 10, maybe we can then XOR this with all of hex 10 to make this become 0. But I can't remember exactly why you want a zeroing IV. I should know that I'm the start of an amazing side journey in life. Oh, thank you very much, The Reckless. I really appreciate that. Let's, Now, I am remembering one way in which the NCC group code was structured. Is that going to be important? No, I don't think it's necessarily important. Let's attack the last block. We should be able to leak the last block using a pattern similar to this. We've just got to wrap it with another loop. If we refactor this to J, for I in range over block size, now we've still got to handle this case where for the first byte we can get 2 possible values. And I don't like this double loop. I'm kind of inclined to wrap this into a function. Yeah, maybe. Let's do this the nasty way for now. We can think about reshaping it later. For I in the range from 1 to block size plus 1, we need to multiply this -1 here. Hang on, I'm just curious how Python works. A, B, C, D. If we go A from 3 onwards, we get D. From 4 onwards is empty. From 4,000 onwards is also empty. Okay, that's kind of not too bad. CT new. Empty bytes.join. Yeah, we need all these. We still need to give all of those. This is our second to last chunk. Instead of going up to -1, we do -1 times I. And then we put in our J. And then we append to that CT chunks, our second to last block, from -1 times I onwards. Yeah, this is getting awful. We're going to have to really tidy this up sooner rather than later, probably. No, this is not really going to work. This is not going to work. How do we lay this out? Create a function, attack block. Does that make sense? Not really. Tell you what, they weren't wrong when they said these challenges are moderately difficult. I mean, I know we can look up solutions and spoilers, but I'm trying to remember how to do this from kind of more first principles. I've got an idea, right? So if we start blasting this second to last block, the last byte, we're going to get 2 ways in which we can have it be such that when it gets fed forward and then the XOR spikes this last byte of the last block, there's going to be 2 ways in which the padding is valid. Hang on. No, hang on. With me doing it this way, one of these iterations was causing CT to not be changed at all. Whenever J was equal to the last byte of the last block, it wasn't, or the second to last block, it wasn't changing anything. That's why we're getting 2. But there are cases in which you can get 2. Is it when it can be 0, actually? Which begs the question, how is that CTF challenge I did broken? Maybe that CTF challenge wasn't broken. Whoops. Because this only would have returned one thing. Interesting. Anyway, we basically spike this byte here until this byte here becomes 1. And then we XOR whatever we spiked this into with 1, and we know that that would cause it to become 0. And then we can XOR it with 2 to make it be 2, and then aim for this to become 2. Aim for this to become 3, aim for this to become 4, this to become 5, and then fix up the last bytes as needed for each of those. And eventually we find out something that we can XOR in with this until they all become hex 10. So it's kind of like divide and conquer. And once we know we have to XOR in to make it all become hex 10, we can recover what the output of this block was. But then how do we attack this one? I guess you make all of these be hex 11 and try and spike this one using this until this becomes hex 11. Send them all to hex 12, attack that one until it becomes hex 12. Or once you can recover this block of the ciphertext, you can recover that. You can just basically truncate the ciphertext and restart the attack on this block. That makes more sense. And once you've recovered this block, truncate it here and do it again to here, and at that point it's the IV you're using to do the same attack. And when we're attacking this one, do we even need the rest of these while we're attacking this one? No, because all this output here doesn't influence this block in any way. Yeah, so we can actually just basically, given... In fact, we don't even need the IV. Yeah, I think we just, given this, we can attack this without even having that. Yeah. Alright, so now what I want to do, I think I want a new function which is attack block. I think that was a good idea. And the block is going to be bytes. It's going to return bytes. We really need to document that. Block is going to be a block of CBC ciphertext. And it's going to return. Is it going to return the plain text? I think it can return the plain text. Plain text of the block of ciphertext. This function. Given a block of ciphertext. No, we don't even need to describe it. Those parameters are enough to describe how it works and what it does. Let's return empty bytes. Do we even need to go right to left on this? I don't think we do we? We'll just go left to right. We can attack this block here. Ignoring this to the right, we can just attack this. We don't even need the IV. We can just start with empty IV and basically feed it in here. We can recover. Yeah, I'm pretty sure I can recover that. Alright. Let's comment this out for now. We might need it. I think all we're going to do is... I don't even think we needed the IV ever. If we don't need this, we can remove it later though. All we're going to do is return empty block.join, attack the block of block for block in CT chunks. So this here can work left to right, attacking each block, and then just concatenate plain text. So now we've reduced the problem down to just attacking block at a time. So here's where I think just logically a zeroing IV does make sense. Zeroing IV is going to be empty list of integers. No, because we want to be able to prepend, so we will do a deck. From collections, import deck. I think I'm attacking this a bit of an unorthodox way, but it just makes the most sense in my head. So the zeroing IV is a deck over integer, or deck of integer. Pull in that name. Yeah. This attack over the blocks needs an oracle as well. It's an oracle that takes bytes and bytes and gives bytes. Oops, it's a callable. Why are you squiggly? At param oracle, a CBC padding oracle that returns true given good padding, else false. Now for I in range of length of oracle, no, block. What are we going to do? Remembering that the last byte of the block is a special case because it can have two different, successes. All right, my brain's a little bit fuzzy. I'm going to take a quick break to have a think about how I'm going to approach this. So go grab yourselves a glass of water, stretch your legs, grab yourselves a snack, and I'll see you on the other side of a short break. Alrighty, we are back. So, at the very least I've thought one step ahead. So, yeah, for each of the positions in the block, maybe we won't even need I, we'll see. Prefix, helps if I focus the right window. The prefix is going to be the block up to the block size. I know I'm reaching out for a global here. Minus the length of the zeroing IV minus 1. So when zeroing IV is empty, that's going to be 0. So 16 minus 0 minus 1 is 15. Block up to 15. So like in this case, A up to 3 is the first 3. So we're chopping off the last one. Good. Yep, so that's the prefix. And yep, that's fine. And for J in the range of 256, no, J in the range starting from 1, counting up to 255. The spike is going to be block up the block size minus the length of zeroing IV, the byte, XORed with J. Yeah, so we're gonna basically, in the case that like the first time through we're aiming at the last byte, the prefix is going to be everything except for the last byte. The spike is going to be the last byte of the original block spiked or XORed with 1 through FF. That's got to be 256. That's the spike. And then the suffix is always going to be block from block size minus the length of zeroing IV plus 1 onwards. Let's go block is equals bytes 16. So 16 nulls. Zeroing IV starts off as empty. So the prefix is going to be this. The block size, whoops. The block size is 16. So this should be 15 nulls. Oh, this mouse, I tell you what. This, is that 15 nulls? It is. You know what, I'm going to do block equals, no, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so that's 16, good. So the prefix is going to be 0 through E, that's what I want. Our spike is going to be targeting the F. Ooh. Chur 70 should be F. Yep, good. Okay, so I had an off by 1 here. Subtract 1 there. So spike targets the last byte the first time through. The suffix the first time through should be empty string. I had another off by 1, I think. Get rid of that. Now the second time through, the zeroing IV is going to have some meat to it. So the second time through, the prefix should be everything except for the E and the F. Good. That is everything except for the E and the F. Good, we're on track. The spike should be E at this stage. That's the E. Good. Nice, by the way. Can I get some nices in chat if anyone's around? And the suffix should just be the F at this stage. Yeah, good. Good, good, good. Then once we append to our zeroing IV again, the prefix should be everything but the D, the E, and the F. Yep, good. Yeah, this is making sense. I think we're good. We've got the prefix, the suffix, and the spike. So now, padding is correct, is gonna be, so here we've got our IV is gonna be our prefix and our spike and our suffix. Padding is correct is gonna be oracle over the IV and the block. By the way, this block size, we don't need that to be block size. That can be the length of block. You know what, we can calculate block size is the length of block. You don't actually need to reference that constant anymore. Oh, I've messed that up really bad. Padding is correct, is oracle over the ivy and the block. Why are you angry? Hang on. Ah, because the spike is an integer, so we need to do bytes over the spike. Good, the yellow goes away. If padding is correct, print J. And once this loop ends, let's just return. So we only do this loop once. Actually, we don't need to else that. So do we see one or two things appear in the output here? We get an error. Great. Because attack block requires an oracle. Yeah, it takes an oracle and a block. Good. Why are you yellow? Because this is not bytes, it's bool. Bad type. Good. We get 3 things there. That's not what I wanted. Who's printing? Who's printing? I've only got one thing printing. And we're always printing 3 things. That's not what I wanted to see. Let's print J and let's print that IV. They're drastically different. What's going on? Oh, because we're probably running attack block multiple times, aren't we? Let's return empty, but let's just do attack block over using the oracle, and block is just the first block. Run it again. Okay, now we only get one thing, but I'm pretty sure 2 things can be printed here. I'm pretty sure that's like a common thing with padding oracle attacks. When could this light up twice in the last byte of a block? Could it be when it's 0 or 1? Was this wrong of me to change unpadded to do that? Let's actually read the spec for PKCS7. Is there an RFC for it? Is this what we get for it? Let's have a read. So you pad the input with k minus L mod k octets, all having value k minus L mod k. That's basically the mathematical way of describing PKCS7 padding. So it's kind of implied by the spec that you can't have the last byte be 0. But I'm just worried I'm missing something. You know, I'm going to cheat and I'm going to peek at NCC padding oracle. I just want to understand, 'cause I'm pretty sure something weird can happen for that last byte where two values can come out. Where's the part about? Yeah, okay. No, wait. Tiny edge case, this is what it is. Suppose the plaintext penultimate byte is already set to 2. In this case, the message's padding would be valid if the final byte is set to either 1 or 2. If our search hits 2 before 1, but I can't hit this case because I'm building my spike by modifying that byte. So it's never going to come out to the case where, suppose the plaintext penultimate byte is already set to 2. Oh no, wait, I can hit that case because I'm not brute forcing something that's necessarily padded. I'm attacking arbitrary blocks. Okay, yep, no. Because I'm attacking from the first block onwards. So if this byte here, because this is not necessarily padding data. So if this second to last byte was 2, or if the second to last byte was 3, and the third to last byte was 3, or if, you know, 444 or 5555, then as soon as I spike this, hang on, I can't be using my spike pattern because I'm not necessarily attacking padded data. So the spike is not that X or J. Yeah, this has to be all of the possible 256 values, and spike is J. So change that to J. Yep. Cool. No, that makes sense, that makes sense. But if I'm attacking this and this happens to be 2, then there's 2 possible values for this last byte that could result in not a padding error. And there's a trick to disambiguating them. And it's basically to move on to the next byte, and if you can't win at it, go back to the last byte and try the other option. So you do like a depth first search and you backtrack if it breaks, but you only need to have for the first 2 anyway, so it's probably not worth doing depth first searching. Okay. So, stop it. For J in the range, spikes is going to be a list of integer starting off as empty list. Stop it. If padding is correct, spikes.append J. And it's probably good form even if we're not working on, it's a little bit more expensive to attack, but we should probably just always check to see if spikes, because for the first time through this loop, spikes should have either 1 or 2 things in it. For every other iteration, it should only have 1 thing in it. But as a bit of an error check, we can just always check to make sure what spikes has and do the whole key space. You know what? That's a bad place to initialize that. It should be outside the loop. So after this loop is finished, if the length of spikes is 1, then we need to the zeroing IV, we need to append left. So we're working right to left, so we need to append to the left. J, X, or I? No. Spikes 0, X, or I. Why are you squiggly? Good, you're not. We basically need to get whatever was in spikes and XOR it with... No. Where are we using I? Nowhere. If we start I from 1 and go up to length of block plus 1, because the first time through the loop, first time through this loop, whatever we ended up with in spikes is going to be the XOR of hex 1. If we XOR it with 1, we're going to make it be 0. The second time through the loop, whatever we end up with in spikes is going to be what caused the plain text to end with 2, 2. Thus, whatever's in spikes caused the second to last block to be 2. If we XOR it with 2 per I, then zeroing IV is going to end up being an IV that causes the output of the oracle over the block to be all zeros. That kind of makes sense. And if the length of spikes is 2, to do, let's just pass. Else, if spikes is empty, or it's basically if spikes is anything but 1 or 2, we've got to raise some sort of error. What sort of error should we raise? Value error. That'll do. Failed to attack oracle over the given. Failed to attack oracle over the given block. And then we'll just basically emit the block. So if the length of spikes is 2, and I equals 1, because it's the first time through this loop, then we have hit the quirky case where block minus 2 equals 2, or block from minus 3 through to minus 1 is 3, 3, and thus we have ended up, I don't know how to word this, or ... We need to disambiguate. And how do we disambiguate? Because it basically means we need to attack the next byte back, which is kind of gross. Kind of gross in as much as if we just like copy pasted all this code, fine, but I don't want to copy paste code, so how can we structure this? Like, I'm inclined to make this recursive in some way. Yeah, let's make it recursive. Zeroing IV is a deck event. It's an optional deck event. See, the thing to be reminded about, the thing to remember as well, this function here is actually buried inside our function. So it's not really like a public use function. We can make its signature as disgusting as we want to make it, because nothing else will be calling it apart from our encode. So zeroing IV is an optional deck of int, which is by default none. Zeroing IV is going to be zeroing IV if zeroing IV is not none, else empty deck. And I don't think we need this loop anymore. Oh, yuck. Yuck. We're calculating block size based on block. Oh, this is getting absolutely feral. Block size is an integer, which means we need to provide it here. Block size equals block size. We can safely depend on block size here because we depend on it here anyway. We'll get rid of that. Maybe that didn't actually need to be done anyway. Yeah, no, it didn't need to be done. That's fine. We can undo that. Wasn't important. Do we need this? Do we need I? Because I can be calculated from the length of block size anyway. No, the length of zeroing IV. I think we get rid of this here. Let's go 17 down. Clean this up. So attack block. That I think I'm still happy with. For all possible J's, build a new IV. I'm going to call this new IV. Or I'm going to call it spiked IV. Hang on. What am I doing? What am I doing? It's attacking this block. Oh no, wait, the spiked IV prefix is... Why am I using block as my IV? I shouldn't be doing that. This is completely wrong. I shouldn't be using block as the IV anyway to attack the block. Prefix is going to be a whole bunch of zeros. It's going to be bytes. If we just do like bytes 5, we get 5 nulls. Yeah. It's going to be bytes to block size minus the length of zeroing IV minus 1. Length of block minus the length of zeroing IV minus 1. Because length of block is going to be 16. Minus 0 minus 1 is 15. Yep. Good. Prefix is that. Suffix. What is suffix? The suffix is the zeroing IV XORed with the round we're on. And the round we're on is the length of the zeroing IV plus 1. Oh no, it's just getting gross. Suffix is bytes of B for B in zeroing IV, but it's B plus the length of zeroing IV plus 1. Because like when we're trying to get it to be 2, yeah, I think that's right. Oh goodness gracious, this is getting gross. Yeah, so our spiked, that's fine. For J in the range of that, the spiked IV is the synthetic IV with the spike at the position we're attacking, and the suffix is basically zeroing IV bumped up a bit. That's fine. Padding is correct is that. If the padding's correct, we append to spikes, J. Now, if the length of spikes is 1, so we're doing recursion. Oh wait, zeroing IV. We're mutating. Oh, that's really gross, but fine. We can mutate this safely, I think. I'm surprised that the linter's not yelling at me for doing that though. Okay, I can see I'm using iron a couple of places, so I'm going to actually calculate that. Yeah, that's fine. Oh, my brain's completely breaking. You know what? I'm going to take another quick short break to catch my breath. I'm still recovering from a cold, so my brain's not quite where I need it to be for this challenge. So I'll take a break, and I'll see you in a couple of minutes. If we can't start making progress on this soon, we might have to shelve it for another stream. But let's keep trying and see how we go. But for the meantime, I'll catch you in a couple of minutes. Alrighty, we are back. Yeah, this is a tough one, isn't it? That's right, I was going to pre-calculate the round number. So the round number is going to be... You know what? Nah, I won't bother. I'll just keep using the length of zeroing IV. So now here, if the length of spikes was 1, we're going to append left to zeroing IV of the spikes, XORed with the length of zeroing IV plus 1. And then we want to recurse. Well, actually, if the length of the zeroing IV equals the length of the block size, to handle this. Hang on. Wait, is that even going to give me plain text? Not if I can't see the output of the decryption. Damn it. I don't think that's even going to work. Hey, at least we'll have a zeroing IV. Maybe this isn't going to return the plain text. Maybe it's going to return the zeroing IV. Look, if we get this print to happen, I'll be happy. And just return empty bytes. If the length of zeroing IV is not yet the block size, we need to recurse. So we need to return, attack the block, with the oracle being oracle, the block being block, and the zeroing IV being the zeroing IV. Now, if we get to the length, if the length of the spikes was 2, we've hit the weird quirky edge case. And it's not I equals 1, it's if the length of the zeroing IV equals 0. So we haven't started building that zeroing IV yet. We're like, damn it. Hit the weird edge case. So, this value error. Oof, I don't know, I don't like that now. I think we need a special exception. So the class of padding oracle tack exception inherits from exception. Yeah, we've got a new exception now, so we can raise that instead and specifically catch that. This here is not a value error, it's a padding oracle attack. Not exception, that should be error. That's an error, good. We raise the padding oracle attack error. maybe maybe this will work. We'll see. Okay, so we get to this weird edge case. We need to disambiguate. So we're going to try to return the attack with the oracle being oracle, the block being block, and the zeroing IV being, can we do deck over spikes 0? Why am I getting a red squiggly? Why are you unhappy? Oh, I need to accept. If we accept the padding oracle attack error, try the other spike. This is try the first spike. And in the exceptional case, we try the second spike. So that should because won't the second time through, won't the faulty one also win? I think it will lead to a win. Let me have a think about that. No. No. The faulty one won't lead to a win. Cybercard had to go before. How am I going? Not well. Not well. This is a tricky one, this one, and I feel like I've tied myself into a couple of knots with this code, but I'm sure you know what it's like when you've got bad code upon bad code. Throwing more bad code at the wall till it works, never a bad idea, right? So we're crossing our fingers and hoping it's going to untwist itself at some point. Because the coding will continue till the padding improves. That's exactly right. Because the bad one out of these two won't work, because where am I actually? Here, the suffix is going to be bytes b plus the length plus 1 for b in. Yeah, so that's going to make sure that the bad case here definitely results in a padding oracle attack error. So we're just attacking one block here. What if we run? We get our padding oracle attack error. Lovely. How far are we getting? Let's just print 1 here and print 2 here and print 3 here. 1, 1, 3. That's interesting. So we're getting 2 of those, and then the error's getting raised. I kind of wasn't expecting that. I was expecting this to be our problematic path. Huh. Wait, is it not B plus that plus 1? No, this should be XOR. I think that should be XOR. Maybe. Do we get further? We get a lot further. Okay, all right, I'll take it. We're getting to our part where we've actually built a successful zeroing IV for that block. So now what does that actually give us? If we print bytes of the zeroing IV, does it look anything like plain text? Nope. Okay. Alright. I was not expecting that to work at all. So we've successfully manufactured an entire IV such that when it XORs out of here, this is all hex 10. So now do we just XOR this? No. That applied there gives us all 0. So really, isn't this supposed to be plain text? Because it don't look like it to me. We've got some wildly small values like 3 and some wildly big values like 9D and D3. What have we... Okay, so now we're like the dog that caught the car. We've got an IV such that when you XOR it against this, you get all zeros. Doesn't that mean that we've actually revealed this? It just doesn't look interesting. See, now I'm really pushing my understanding of where to take this attack next. So I knew about this trick where you kind of work through divide and conquer and use the padding errors to learn information. I just don't know what I've learned. What was I passing in? CT chunks 0. Yeah, so I definitely attacked this block here. Like, I'm convinced I've learned what the plaintext was, but clearly I have not. Yeah, there's some wildly differing values. They're clearly not plain text. And if we just like take a peek at the oracle, yeah, the plain text is readable. But interesting that it starts with a whole bunch of nulls. Or no, there's zeros. Mouse is screwing up. Yeah, they're probably zeros. They are zeros. What have we leaked? What if for giggles we do this? Let's not return until we do something else. If we do the oracle over the IV, no, the zeroing IV plus the block, do we get zeros there? Step, step, step in. Why did you not step in? Excuse me? Step, step. Step into. Why are you not stepping into the oracle? Does the debugger not like stepping into stuff that's been like passed by reference, or a function that's been passed by reference? Okay, let's... No, the oracle definitely doesn't want to reveal their secrets at all. Okay, so we hit that breakpoint. What if we now set a breakpoint on our wrapped oracle? What if we set a breakpoint here and continue? No, we've got an exception. What was the exception? Ah, whoops. Okay, we've got to do bytes over the zeroing IV to get an actual bytes. And now we debug. Don't want that breakpoint yet. Continue. Now we set the breakpoint here. And continue. And we get another exception. What is it? Okay, the wrapped oracle wants a ciphertext. Am I not giving it to you? No, because I'm not giving you an IV. That's right, because this is a wrapped oracle. Okay, we debug. We don't want you yet. We continue. Step, step. Now can I step in now that things seem to be a bit more straightened out? Okay, yeah, we can. We step into, we step into. So we're decrypting a single block. With the IV being, I think that's a zeroing IV. That's our original block. Now if we step into the CBC decrypt, get our plaintext, our previous block for chunk, plaintext.append. Yeah, plaintext is all zeros. Yep, so our zeroing IV is definitely causing this AES block cipher operator to emit all zeros. Am I wrong? Plaintext.append the fixed XOR of the AES decrypt with the previous block. And we gave the previous block. Yeah, how is our zeroing IV not the plaintext? I'm going to redo this debug and do a bit more stepping in. Breakpoint goes there. Step in, over, in. Over. Now here I want to step into the AES decrypt. We're actually not getting a copy of what this returns. Boo. Over. Dang it. Either way, fixed XOR. I'm pretty sure that's our function. Yeah, take 2 bytes arguments of equal length, return their XOR. Yep, so we know that because plaintext gets a whole bunch of zeros appended to it in a moment, if we step, because plaintext is all zeros, that means that this here and prev block were equal. And prev block is that. But that doesn't look like plaintext to me. Might have to reach for the spoilers soon. How is that manufactured IV which causes this to end up being 0 not equal to that? Ciphertext goes in. It does feed forward, but it goes in and pops out and then... We probably need to XOR it with our original IV. Yeah, we need to XOR it with the original IV. Of course. To find out what the... Yeah, no, good. We need to do the feed forward ourselves manually. Okay, no, I'm alright now. I think we're fine. Where's all my silly breakpoints at? Okay, breakpoints are cleaned up. Alright, yep, no, we've still got to feed forward the IV. So the zeroing, so the zeroing IVs is going to be attack block over block for block in CT chunks. Good. So now we're going to have a whole bunch of zeroing IVs. Now we've basically got to prepend that with the original IV, pairwise them, XOR them, and out pops plain text, maybe? let's grab our pairwise. Python data tools. Detox Mango, have you ever played poker before? Friendly games, and I'm really not good at it. For me, poker is a good way to catch up with friends. It is not in itself a fun game, not for me anyway. I really should just go and chuck this pairwise into my util at this point. I don't know why I keep copy pasting it from places all over the code base. To do look up all copy pastors of pairwise and use this instead. Detox Mango, do you play poker, do you? Okay, good. So we've got our pairwise. So we need to pull it in. Good. Cyberkiter, what? Can't quite make out your emoji. Are you having dinner, are you, Cyberkiter? Oh, spaghetti, yeah. Ouch. You're not wrong. My code base is a lot of spaghetti. Detox play with people in high school. You didn't know what you're doing. Yeah, I never know what I'm doing with poker either. Okay, so we've got our zeroing IVs. And then our plain text is going to be empty list for now. For A, B in the pairwise over our IV, like our original IV, and we'll unpack our zeroing IVs. Probably get rid of those. Can I get rid of those? No, I can't get rid of those square brackets. Well, we'll build a list in memory, that's fine. I'm sure we've got the bytes to spare. Plaintext.append. We need to pull in our fixed XOR. What a mess. Plaintext.append the fixed XOR of A against B. And then plaintext, because what does attack block return? Bytes. So zeroing IV is going to be list of bytes, because IV is also bytes. So bytes against bytes, that makes sense. So PT is going to be a list of bytes. And we return empty bytes.join the plaintext. If we run this, do we get plaintext? No, we get an error. All of our to-do handle this. We don't need that. Why are we returning empty bytes? The length of that equals that. Yeah, okay, cool. Get rid of that, get rid of the print. We no longer need to do Oracle, that was just debugging. We return the zeroing IV. Okay, so this attack block doesn't return plain text. It returns the zeroing IV of the block of ciphertext. So now that we're returning expected bytes, okay, we need to do a bytes over the top of it to realize like the deck into an actual bytes. Yeah, optional deck event. What was that error I was getting? That looked weird. Expected bytes got union of deck over int or deck instead. Okay, that's fine. I thought I might have had like weird mixed typing going on, but deck over int and deck, I'm happy for those to be considered interchangeable by the linter. Fine. Empty bytes. That should never hit anymore. I don't think that this can. So this function here, we've got for, if, elif, else. Yeah. So that I had like an empty return empty bytes. That's dead code now. Now if we run, do we get plain text? Nah, we get a bunch of ones though. We can get rid of these print 1, 2, 3. We don't need those. So we're returning this attack. No, this return is for the leak function, which returns bytes, which I've said is the plain text corresponding to IV and ciphertext. Good. That looks like dead code. That can go away. Plain text equals that. That's fine. R equals that. Ciphertext chunks IV. I think this can go away. Got our wrapped oracle, we've got our PT, and here's our print. That's why we weren't getting plain text. If we uncomment that, oops, I've got angry red underlines. I deleted stuff that was actually important. Yeah. This can go away. But our leaker does need that IV and ciphertext. Okay, so that can't be deleted. Print the plain text, run it, and watch binary garbage fall out. Yep, there's our binary garbage. We got the first block. We didn't get the rest though. Is it my pairwise stuff that's messed up? Just to follow through. Cyberkiter, it feels like it's close. It feels close. Yeah, my pairwise stuff was not appropriate. I think there's a problem here. Feels like it's the home stretch. I'm going to take a quick 5-minute break. Please take an opportunity to grab a glass of water, stretch your legs. I'm wanting to wrap this up pretty soon, but I'm fading hard. So I'm going to take a quick 5 minutes and let's see if we can't get this working on the other side, hey? I'll catch you shortly. Alrighty, we are back. Let's see if we can't get this done. So I've come up with a list of zeroing IVs. What does that mean? In fact, can we pull this across and look at both at once? Come on, pop out. Come on. New window. Thank you. Where's our CBC? Okay. This is really hard to see. So we've got our list of zeroing IVs. The first zeroing IV is something that causes this XOR here. So the first zeroing IV goes in place of our IV here. The first zeroing IV is something such that that XORed with it is 0, which means that our zeroing IV equals that. So we XOR that with that. First block of plain text looks good to me. Our second zeroing IV, ignoring all of this, is something such that that XORed with it is 0. Therefore, our second zeroing IV is that. And so we need to XOR that with the first block of ciphertext, not with the prior zeroing IV. So it's our manual worm pattern that we've screwed up. You know what? That I've screwed up. That's not the fault of anyone in chat. That is, I'll take the blame for that one. So the pairwise is not correct. We need to match up the IV with that. And then that with that. So really, do we need to zip together? Hang on. Let's do for A, B in, let's comment this out. Let's try again. For A and B in zip of, go away, help text. IV plus CT against our zeroing IVs, pt.append fixed XOR of A and B. But I feel like these are different lengths. Because IV plus CT, we get 1, 2, 3, 4. But the last block of CT doesn't need to be on the left-hand side of this zip. So CT through -1. So if we zip together the IV and then all but the last ciphertext with our zeroing IVs and XOR them together, now are we good? Now if we run it, do we get plain text? we get an error. So one of A or B is not a bytes. Which one is it? We've got to zip together a list of IV and then unpacked ciphertext through -1. That looks a bit better. So on the left-hand side of our zip, we've got a list. First element of the list is the IV, which is bytes. Yep. And then CT. Oh no, CT is also bytes. That doesn't need to be CT, that needs to be CT chunks. Yeah, that makes more sense. So the left-hand side of our zip is a list. IV, and then each of the chunks except for the last chunk. And then the right-hand side of the zip is a list of bytes. Run it again. And we get plain text. Cool. It's got padding, so we probably need to unpad it, right? So pull in our unpadder. Whoop. Yeah, so here we need to just unpad. Whoop, no. Where are we? Run it again, and we get something that looks like sensible plain text. Now, we were meant to randomize this choice, but you know what? I don't want to randomize the choice. I want to get the plain text for all of them. If we do randomize the choice, we end up with this. Play. Cooking MCs like a pound of bacon. Play. I'm on a roll. It's time to go solo. Cool. Looking good. But really, I want to do this for each of the lines. So we could do for PT in lines. Oh, we're reusing a variable name here. PT is. That should never have been PT. That should have been CT all along, right? Yeah, it should have. No, it was a plain text. Because we were telling the Oracle to encrypt it for us. Yeah, so I don't like the reuse of that variable. Let's fix that quickly. So challenge is going to be that. No, flag. Call it a flag. So the Oracle takes the flag, and then the plain text is the leak, and we print the plain text. Good. For flag in lines, attack it, and let's see if our Oracle works given all the flags. Error. We've got a base 64 to code it. That's right. Flag is Does that work? There we go. All right, our padding oracle looks like it's working for all the inputs. Beautiful. I'll clean that back up so that it respects the original challenge. All right. Now, do we need a test? This bad code can be yeeted. Leak the plain text from the padding oracle. We could probably write a test here. Yeah, let's write a test there. And then we'll call it a night. So the oracle is a padding oracle, but it needs a plain text. Yeah. The plain text is going to be hello world. No, hack the planet. So the oracle is a padding oracle over the plain text. Oh, and then we need to wrap the oracle. Yuck. Let's figure out how to wrap it in a single line. So then if we... let's do... flag is that. And then if we leak the PT, where the oracle is, excuse me, lambda xy, because this oracle here takes, excuse me, this oracle takes the IV and the ciphertext separately. So it's lambda xy gives oracle dot decrypt. Yep, decrypt and check padding. Thanks PyCharm for not auto-completing that for me. X, Y, because decrypt and check padding takes, oh, just the ciphertext. So X plus Y. Yep. So we smash X and Y together. So this is just basically like it's the same as this wrapping down here that I did, where it takes the IV and the ciphertext separately, smashes them together. This lambda nonsense is just me squeaking that onto one line. So leak takes the oracle, takes an IV and a ciphertext. Gross. This is really gross. This test is disgusting. The ciphertext is going to be the oracle.encrypt, which doesn't take any values. Good. CT chunks. I can't type. Is the chunkify over CT to the block size. This is awful. IV ciphertext is going to be CT chunks 0 and CT chunks from 1 onwards. This leaker then gets given the IV and the ciphertext. And we get the PT out. PT equals the flag should give us true. Run that test. We'll run all the tests. Come on. Thanks. The flag's got to be bytes. Is that all I had to do to get that working? Of course not. We have to realize this generator. Try again. IV equals IV, CT equals CT. It wasn't happy that I was basically doing oracle equals before I was doing some non-named arguments. Oh, isn't it terrible when your tests don't pass because there's a syntax error in your tests, not in the actual code? Can't concatenate list to bytes. What? This here's got to be empty bytes.join over the rest of the chunks. Good. We'll get there. Eureka. Okay, good. We've now got a test that demonstrates the fact that this padding oracle attack works. Deep breaths. So let's go back to the challenge and do a really quick recap, and then I'm going to go lay down and rest. So we generate a random AES key and we use it across all encryptions. We pad the string and CBC encrypt it. Good. And we leak the ciphertext and the IV to the attacker. And our oracle also consumes arbitrary ciphertext from an attacker, decrypts it, implicitly checks its padding because our decryptor always unpads in a strict mode, and returns true or false based on whether the padding is valid. So we built our oracle. We then decrypted the ciphertexts by doing a padding oracle attack. What does that roughly look like? First of all, we just check to make sure that the oracle, when you tell it to decrypt the IV in the ciphertext, does not raise a padding error. Because if that doesn't hold, the attack's never going to work. As an attack function, you were given bad data or a bad oracle. And we basically work from left to right over our... Where's CBC? There's CBC. We work left to right over our ciphertexts. And we build what's called a zeroing IV. And it's an IV such that, for say this block in the middle, this block of ciphertext here, it's an IV such that when it gets XORed after the real ciphertext block gets put through the AES machine, results in all zeros. And the way we do that is basically by having a synthetic IV go in and try all 256 byte values until we can cause that last byte to become 1 after it's gone through the decryption and after it's gone through the XOR. Sometimes there's a weird edge case where it can be 2 if the second to last byte was also 2. Once we've got that to be 1, we can kind of repeat the same activity until we can cause the last 2 bytes in the bottom here to become 2, the last 3 to become 3, the last 4 to become 4, and so on. And in each time through that loop, we're building up that synthetic IV or zeroing IV such that once we're all done, we know something that can be XORed in here, that once XORed against this, I think I just made a complete hash that. We know something that once it gets XORed with this, produces all zeros. Which in essence means we know what came out of here. Because if we know what to XOR that to make 0, something X XOR X equals 0. Where X XOR something equals 0, both things on the left hand and the right hand side of the XOR are the same. So we can basically leak the output of each of these blocks in the middle. And then we just need to basically get the original authentic IV and XOR it with our first zeroing IV, which was really the output of this, and we learn the first block of plain text. We then get whatever was going into here and XOR it against this ciphertext, I think, to get, we whatever we found we could XOR against this to make 0, we XOR against this block to get that block. And we can, basically with a Boolean response out of the oracle as to whether we get the padding correct or not, we can divide and conquer and then do XOR horrible things, and out pops plain text. So it's a classic attack, and I have made a complete mess of demonstrating it, I'm sure. I can't recommend this article by Cryptopals enough. Cryptopals exploiting CBC padding oracles. So I'll drop that in chat if anyone wants to see a proper explanation of padding oracles. And I'll be certainly reading this after the stream to kind of be like, now I remember how it's meant to be done and how it's meant to be explained. But either way, I hope this was helpful. I hope you enjoyed watching me stumble my way through it. Before I go, Cyberkiter, are you streaming this week anytime? because we caught your stream on Saturday, and I really loved it, and I'm keen to tune in for the next one. Do you have your next stream scheduled yet, if you're still around? Saturday. Awesome. Okay, cool. Well, I'll be tuning in Saturday, and for anyone else who is here or watching this on YouTube, make sure you give CyberKaida a follow on Twitch. They put out brilliant stuff, so I'm looking forward to that one. But that's it from me. I'm not in the mood to raid anyone because I want to go lay on the couch and ease my head and look after myself. So until next time, I hope you stay well. Hope you have a fantastic week. Thanks for sticking this one out with me this evening. It was a bit of a rough one. And until next time, I hope you enjoy the rest of your week. Bye for now.